Assalamualaikum and good day to all. This lecture is about process and process selection. Most of the process you have learned is already in the manufacturing process course. In this case, we will learn how to choose the process based on the design requirements, selected materials, precision surface condition, batch size, and many more. Here is the outlines for the lecture. The introduction and synopsis, classifying process, the process, shaping, joining, finishing, processing for properties, systematic process selection, ranking process cost, computer-aided process selection, summary, and conclusion. Before you start with the process selection, you must master the design requirements, okay? Design requirements and the translation over here. Similar to the material selection, initially you need to decide the design of the product based on the design selections. So prior to this, the design and material selection need to be done first. As for the process selection, all these inputs are required, which is the function, shape, and materials. All these factors, function, shape, and materials are related to each other. When one of these factors is changed, then the process selection is need to be changed consequently. So the process attributes for the process selection will be material, shape, size, minimum section thickness, tolerance, roughness, minimum sections, batch size, and capital cost. In the process universe, you have shaping, joining, finishing. Each of the class of the process has its own members. And then from raw materials, okay, you need primary shaping, okay, which include casting, molding, deformation, powder method, specific method. Then you have secondary shaping, which is including machining, heat treatment. And then the joining, and finally finishing. Usually the primary shaping is done by the manufacturer, such as sheet material using rolling machine, tube material using extrusion, metal block using casting machine, and secondary shaping is involving machining, drilling, milling, laser cutting, and many more to change the shape into a specific component design. After the components are made, the combination of the components into one product combination or the assembly of the components into one product, which is need to undergo joining process. So joining process includes adhesive, welding, rivet, fasteners, and after the joining of all components, finishing process are required according to the design requirement. For example, surface finishing of SA 2.5 is by using machine grinding and sandblasting according to ISO standards. So figure 7.3 shows the taxonomy of the kingdom, okay, of the process which part of the shaping family expanded. Each member is characterized by a set of attributes. Process selection involves matching these to design requirements. Finally, at the member of the process, you are required to match the process record, including the attributes such as material shape, limitations, size range, minimum section, tolerance, roughness, minimum batch size, and cost material. Over here, figure 7.4 shows the taxonomy of the process kingdom again with the families of joining and finishing. So you need to match all these processes, joining and finishing, which is related to the material joint, geometry, size range, section thickness, relative cost, and so on. All this supporting information is very crucial and need to be used and defined. So over here, for you to just refresh back on in the manufacturing processes, you have the primary shaping, secondary process, and joining and finishing. So this is the answer for the from the previous slides, which is you having raw material, then you have shaping, which is sand die casting, investment casting, and then you have molding methods, injection molding, compression molding, blow molding, and then you have the deformation methods, which is rolling, forging, and drawing, and then you have powder method, which is sintering, okay, hot isostatic pressing, shape casting, and then you have special methods which is rapid prototype, lay up, and electroform. And then also you have machining, which is the secondary. Okay, cut, turn, plane, drill, and grind. And then you have a heat treatment, which is the quench, temper, and edge hardening. And then you have joining, which is including flexible flexible joint, and then you have a rigid joint. And then you have a welding, which is MIG, TIG, solder, hot gas, and bar. And then you have fastener, which is including rivet, bolt, staple, which is I think stable, and then sewing. And then you have finishing, which is you have electro polish, lapping, and then you have burnish, and then you have coating, which is include electroplating, anodization, and also spray coating, paint and print, which is including enamel, pad printing, silk screen, and you have the texture, which is including roll, laser, electro texture. You can select the process starting from the manufacturing process decision to the primary, including deformation, casting, sheet metalworking, and polymer processing. Secondary shaping is machining, then joining or finishing depending on the requirements. We also need to consider the material compatibilities and process capabilities. Last but not least is costing, which include material costs, tooling costs, and processing costs. For example, the end product will be the mountain bike. So you have to select processes to manufacture a bike. So you have tube, top tube, rear brake, rear derailleur, front brakes, and then many of these components need to be fabricated and then attached together. Now, as for the manufacturing process decision, several questions are need to be answered as below. Over here, how to choose the specific manufacturing processes, and then how do the selected material influence the choice of manufacturing process, and then what product function or performance issues influence the choice of process, and then what criteria should be used to select process, and then what is the priority of the criteria, and then who makes the final decision. So each is the manufacturing process decision. Each process is characterized by a set of attributes, which is the material that the process can handle, and what kind of shape that the process can make, and then what is the machine precision, complexity, and size, and so on. Process selection, which is the finding the best match between process attributes and design requirements. Material properties and shape limit the choice of process. For example, ductile materials can be forged, rolled, and drawn. Those are brittle must be shaped in other ways. Materials that melt at modest temperature to low viscosity liquids can be can use casting. Cylinder shape can be made easily by rolling or drawing, but not by casting. Hollow shapes cannot be made by forging, but they can be done by casting and molding. Some of the process will affecting the properties of the material itself. Rolling and forging change the hardness and textures of metals and align the inclusions they contain, enhancing strength and ductility. Composites only acquire their properties during processing. Before, they are just a soup of polymer and sheaf of fibers. Like other aspects of design, process selection is an iterative procedure. The first iteration gives one or more possible process routes. The design must be then rethought to adapt it as far as possible to ease manufacture by the most promising route. The final choice is based on comparison of process costs. Information, for example, case story, histories, documentations, experience, example of process routes for use for related products are required to be used. Design for manufacturing guidelines. So keep functional and physical characteristics as simple as possible because simple and sturdy parts are easier to make and have higher reliability. Design for the low cost production method, which is having critical for high volume parts. Design for minimum numbers for processing steps. So you need to minimize the step of the processing in the manufacturing. Specify tolerance no tighter than actually needed. So the tolerance can be, some tolerance can be loose, some tolerance need to be as tight as possible. Over tolerance design leads to increased costs through unneeded processing efforts and false positive scraps. Part processing sequence. First is the process which is to change the raw materials condition and shape into basic form. So casting, rolling, forging, drawing, molding, and extruding are the most common primary process used in the manufacture. Secondary process, which is to add or remove geometric features from the basic forms, which is altering the material's basic shape or forms, which is including machining, and then you have drilling, punching, and also trimming. Tertiary process is the surface treatment, such as polishing, painting, heat treatment, joining, plating, anodizing, and thin film coating. Common keywords are used such as TOP is referring to electropolish and BOT, which is referring to color anodization process. Then you have the process selection criteria, which is attribute need to be known prior to process selection. So these are the criteria that you need to know, which is the compatibility with selected materials, dimensional accuracy and tolerance, size and weight capacity, lead time, minimum and maximum production quantities, which is the batch number, batch size, and then you have the surface finishing, either it is required or not, and then the need for post-process operation, which including heat treatment. Another factor that you need to consider, which is the cost factor. So the cost can be influenced by a special design features, for example, threaded inserts and dovetail grooves, and then it depends on the material availability. For example, uh, the lead sometimes have a fluctuation of price. For example, in February and also in June, and then suddenly have a drop in September, for example, and then you have to use consider the cost of the need of the special tooling, and then you have a post-process finish operation, special handling equipment, special inspection equipment, and also scrap rate. Shaping. This is the casting, one of the most common process, such as you have learned in the manufacturing practice. Casting requires a mold of product, which include the inlet to pour the liquid into the mold cavity. The mold can be made from sand, carbon steel, refractory, and silicon rubber. The liquid can be metallic, polymer, and such as resin, and also ceramic paste that will eventually harden after filling in the mold. The most common casting method, which is the sand casting. Sand casting requires fine grain of sand, preferably similar size, using sieve. Mold is made either using the exact finished product prototype or molding tools. The if the object is a complex three-dimensional parts, two parts are required separated using a compound such as talc, graphite, and water-based silicon solution. After the mold is set, liquid metal such as tin, bronze, and aluminum is poured into the cavity through the inlet. This process may produce air void. If air is not properly removed, then you have a defect product. To avoid this, multiple inlet point is suggested so that air is easily removed. The slightly advanced version of sand casting, which is the investment casting, which is Introducing the use of wax pattern inside refractory slurry. Metal liquid is poured into the mold and vacuum is applied so that it can fill the cavity evenly. Next is the die casting, where steel molds are used. The mold need to have a male and female molds, and metallic liquid is plunged using a plunger into the mold. Compared to the sun casting and investment casting, die casting can be used repeatedly and faster. The drawback of this method is that it requires a lot of equipment such as compressor, electric motor, and so on. Furthermore, the cost of making more is significantly higher than the sand casting and investment casting. For example, for a 20 centimeter times 20 centimeter times 10 centimeter mold costs more than RM 2,000 ringgit. Ringgit Malaysia 2,000 ringgit. Some mold is very heavy, so you require a winch loader to move around the mold. Low pressure casting combine the mold with the furnace over here. From the furnace, metallic material is liquefied and pushed towards the die upwards using gas pressure, usually inert gas such as nitrogen. The metal liquid fills the cavity could made from the zircon sand and also binder. Some detailed design of the sun casting. So you can see here you have the two molds, sand mold actually, separated by a parting line. And then you have to pour the metal liquid into this inlet over here. Okay, sometimes you need to put a core over here so that you have a what you call a hollow shape, or for example a hole in the object and so on. As for the die casting, okay, molten metal is poured into the inlet over here and you use plunger to push the material molten metal into the mold cavity. So you have the stationary die and moving die, we call it male and female and so on. And then after the molten metal is cooled down to and become solid, and then you have to use the ejector pin so that you can remove the components from the mold. Here is the method to produce mold from wax pattern. So this one is the investment casting. So that first you have to make a pattern tree, sometimes made from wax, usually the one which easily to melt at high temperature. And then this pattern tree is dipped into a ceramic slurry. So after you dip into the ceramic slurry, and then this one will be hardened. And then after that, you pour the molten metal into the hollow ceramic shell. And then after the metal solidify and cool down, you can break the ceramic. You can break the ceramic shell, and then you have the finished casted product. Here is the detailed process for the investment casting. First, you make a mold made from wax, and then you combine into a four-part pattern tree, for example. Then you put the four-part pattern tree wax cast into a container, and then you pour down the hardened slurry. Sorry, actually the slurry first, and then let it harden. Okay, and then you remove the wax by melting at high temperature. Okay, remaining the hardened slurry, and then after that you use the hardened slurry mold, and then you pour down the metal molten metal into the cast, and then after that you break down the ceramic mold, and then you can get the product. Next shaping process will be the deformation method. Deformation method employs both mechanical and heat energy to shape materials. Usually, the material need to be malleable in order to use this processing method. For metallic materials, metal need to be heated to a certain temperature so that it is soft enough to be shaped without changing its composition. In the forging method, heated metal will be pressed using two dies vertically. Okay, you have upper die and lower die. For rolling method, the heated metallic bar is rolled to change its shape and size, such as making I-beam over here. For the extrusion, the material is pushed out similar like to space, and then in the this method, the metal is shaped using a tool while spinning on a pattern mold, such as making a disc plate. This is some example of forging using toast die where it produces flash waste. Okay, here you have the block over here to be inserted from in the upper die and the lower die, and then you ram the pressure over here, and then the remaining material over here will be pushed out to, from the cavity, and then you have a flash end at the cutter. Then over here you can see a sample of the for example this spanner over here have a flash exceeding from the mold. This is the rolling deformation process for the metal. So the formation process, you have rolling, extrusion, drawing, and forging. In this case, for the rolling, you have a thick slab bar, metallic bar, and then you push towards a roller over here, and then from that, from the roller, and then you can get the thin sheets over here. So usually thin sheet material usually made from this process. And then from the roll to the different final shape, you have from ingot, or and then you change it to bloom, and then you put it into a structure, and then either you can put into a slab to make it into a sheet or coil, and also billet to make it into a rod or bar. Then over here is the extrusion and drawing. The difference between extrusion that and drawing, extrusion will be having a plunger to ram up the billet into the extrusion die, while drawing, okay, the billet is pulled out from the drawing die. This is some example processes in for the metal sheet fabrication. You have drawing, punching, shearing, spinning, and blanking. So in case for blanking over here, you can see as this in the figure, metal sheet is held in between the die and the guide plate, and then it will be held by the holding force over here. Then the die having a similar shape as the guide plate, which is having a circular hole over here, and then you put blanking force towards the puncher over here, and then you will remove the material in between this die, and then you can have this kind of uh, product or component over here. Of course, after you do the blanking, you have burr, shear dam edge, and also die roll, flatness, and so on. This kind of the appearance need to be improved after the shaping process. This is the deep metal drawing. Okay, so over here similar principle as the blanking. You have die and also blank holder, and then you have the drawing force which punching towards to the sheet material, and then from here you having a shape over here, not completely removing out the material from the sheet metal, but over here it producing a shape. Okay, so here is the blank, and then here is the drawn part. This is the metal spinning. Okay, the fundamental is that you put the metal sheet in between the back support plate and the S-span part form, and then you spinning the component over here, the sheet metal, and then you have the spinning tool which eventually shaping the object. Okay, so here is some example of the sheet metal being shaped into a form of hemisphere. This is the molding process which is usually used to shape plastic material. Injection molding over here can use raw material in form of granules and binder in a screw feeder forcing into mold cavity. Put the granule polymer over here, and then this one you have a screw over here which eventually mixing and heating of the granule, and then it is being pushed towards a cavity of the mold. The blow molding is the most common method to produce hollow shaped products such as bottle and container. Over here, this method can be applied on glass and plastic. As for the polymer extrusion over here, it is similar as the metallic extrusion method, except it has a pressure screw that melt and compress polymer and granules, and then the extruded product in form of a thread like that. Okay, this is the difference. In the thermoforming method, for plastic sheet is similar fundamental as deep metal drawing and so on, except this one is method is applying heat to the plastic panel and then it being shaped towards to the die. These are the polymer shaping process that use molding method. You have a compression molding, blow molding, injection molding, transfer molding, and also reaction injection molding. So this is the manufacturer setup for the polymer processing method. This is example for the blow molding for producing water bottle. So you have the first one, which is the Patterson extrusion. Okay, Patterson extrusion where you extrude the material from the raw material condition, which is the granule and so on, and then you you push it towards a die head over here, and then it will form into a form of a rod, and then pull down over here, and then it will be compressed with the uh, molded die over here. Okay, for the mold over here, and then over here you having air hose over here, and then the air will be pressurized to blow out the originally rod material over here and then into a shape of a bottle. Then the mold is released to get the final product. This is the injection molding machine, which is similar in our polymer laboratory. So over here you have the injection molding machine. Okay, and then you need a mold and also the ejector pin and die over here. And then over here you are required to put the material in the hopper and then be melt down with the screw over here and also heater, and then push towards the mold cavity. And then after that you can have the product. Over here is the breakdown of the mold. Okay, which including the support plate, ejector box, ejector bar, ejector plate, and mold core, and so on. So that's why the injection molding costs significantly on the mold itself. This is the compression molding. Okay, compression molding, you have the clamp to clamp the sheet material, and then of course over here is the preheated plastic sheet which is having a malleable condition. Then you have the core plug and the mold. So this one is the male and female mold over here actually. And then you apply the force to the core plug, and then you press down the material, and then the air escape from this part over here, and then you can get the finished part. Here is the transfer molding. Okay, transfer molding, which is having a heated mold over here. Okay, heated mold, and then you have ram, and then you have the charge over here. Charge is actually the material that you want to mold, and then you ram the ram over here, and then you have a spruce and parts component over here. Next is the powder processing method. For metal will be powder metallurgy. The first one is the die pressing and sintering over here. The material powder is compacted in a die, often with a binder. Then heat is applied until the temperature that fuse the powder at a certain amount of time. You can see this in the resin mounting machine in our lab, also in the materials engineering lab. Another method is to use a heat isostatic pressing method or HIP method to press and heat the powder into a desired shape with no porosity, such as making the biomedical parts and aerospace part. The powder injection molding over here applies similar principles as plastic injection molding. In this case, metal powder is mixed with the binder, is poured into the screw heater and pushed into heated mold to a desired shape. Then the shaped material is then sintered at high temperature to reduce the pores in the product. And then last but not least is the slip casting method, usually for ceramic hollow shape production. Next is the composite shaping process. The first one is the filament winding, which can produce tubular structures such as water filter tank. Next is the most common composite forming method, which is the hand layout method, usually to produce a low-tech composite such as boats and panel and so on. Here is the advanced version of the fiber and the resin is sprayed on the mold and then roll using a roller as a layout process. For high-tech requirement composite, vacuum bagging is used to remove the excess resin so that you will get the optimum fiber to resin ratio, such as making the aerospace component. Last but not least is the pultrusion method to produce composite section. These are the common methods used for rapid prototype. 3D printer is an example of deposition modeling where you heating the plastic filament such as ABS, then move either the nozzle or the stage to get the desired 3D shape. Next is the stereolithography method, which is to produce 3D plastic shape from a liquid phase photosensitive resin by applying laser beam. Also, similar principle can be used by metal powder using laser sintering method to produce 3D shape metal. Similar deposition modeling, direct molding over here, use paper printing technology to print 3D shape object. Next is the advanced version of laminator, which uses laser to bind polymer and wood paper. Here is the machining shaping process, which all of you should already well versed or mastered of this basic principle of this processing. You have a turning and milling, you have drawing, blanking, bending and stretching, you have electro discharge machine EDM, and then you have the water jet cutting. So basically machining is a material revolving method. So for example, sawing, which is using a tooth blade, milling from a flat surface by a rotating cutter tool, planing using a translating cutter as a workpiece feed, and then shaping from translating workpiece using a stationary cutter, boring, increase diameter of existing hole by rotating the workpiece, drilling using the rotating bit from forming a cylindrical hole. Reaming is to refine the diameter of an existing hole. Turning, form a rotation workpiece, and then facing, form turning of the workpiece using a radially fit tool, and then grinding, which is uh, forming a surface using a abrasive spinning wheel, and then lastly will be the electric discharge machining by means of a electrical spark. That's all for this lecture. Thank you very much.